Olá a todos, bom dia. Então, nós estamos em mais uma transmissão ao vivo para os seminários do programa de pós-graduação em Física e Química do Materiais. Bom dia, professor Horácio.
Bom dia.
Bom dia, Alberto.
Bom dia, professores.
Então, o nosso seminarista hoje é o doutorando, Alberto, Jorge, Baeza, Campuzano. Eu vou fazer uma rápida apresentação do Alberto e então nós iniciaremos o seminário, ok? Bom, então a apresentação do Alberto será em inglês e eu vou apresentá-lo então em inglês. Então, o Alberto é Mexican, mainly from Querétaro City, 3 hours from Mexico City by bus. He grew up in there, and he obtained his bachelor's on civil engineering from the Autonomous University of Querétaro. His thesis was focused on soil mechanisms under the supervision of Professor Maria de la Luz Pérez Raya. Followed by that, he became the head of Soil Mechanics Department from Geotécnica Integral SA. Then he was awarded with a full scholarship, European Masters in Engineering Rheology, on which he started a full year on University of Ljubljana in Slovenia, working with viscoelastic and mechanical engineering. Followed by that, he moved to Catholic University of Leuven in Belgium, on which he obtained his degree on chemistry engineering. In the meanwhile, he took an intense course on rheology at University of Minho in Portugal. Finally, he went back to Mexico to work on a project about rheology of asphalts. In 2021, he started his PhD at Physics and Chemistry of Materials program at UFSJ. So, good morning, Alberto.
Good morning, everyone.
I'm going to put your presentation here.
Okay, go ahead. Yes,
and today,
now.
Yeah. So you have the word.
Now, thank you very much, professors. Thank you very much, Professor Marco. Thank you very much, Professor Horacio. As Professor Marco stated before, my name is Alberto Jorge Baeza Campuzano. I'm from Mexico. Now I'm a PhD student here at the University of San Juan del Rey, mainly in FQMAT. So today's topic is going to be micro and macro rheological analysis of polymers. I decided to work on this because that was something about my master's, and I found it quite interesting for this seminar. So let's begin. First of all, we're going to talk about some content. We're going to have in here the introduction. We're going to talk about like basic meaning of what is rheology. Then we're going to have the current needs, products. Then from there, we're going to have about the bulk rheology and micro rheology. We're going to explain those things quite deep in there. From there, after knowing that rheology mainly involves viscosity, and from there we're gonna talk about how to measure and a deeper understanding. At that case, we're gonna state only just on the Newtonian behavior of materials. Knowing those things, we can move on to non-Newtonian system. From there, after knowing the non-Newtonian system, we're gonna see how the non-Newtonian might stay in steady state and unsteady state. Because of knowing that it's a non-Newtonian, we're gonna have two different states. Keep in mind, those are not chemical states, okay? Those are response states when they are suffering some kind of deformation. Then we're gonna have how to measure the viscosity. In here, we're gonna see something, the torque and the response. I'm not putting the equations of how to measure the viscosity of common models that you will find in the literature. I'm just putting here how to measure the viscosity with the device, because the device applies some torque and you're gonna get a response, okay? Just be clear on that. We're gonna get the results and we're gonna compare with those results in a common graph. After that one, we are talking so much about viscosity and device, response, torque. We're gonna see the device on the market. It's not a huge device, but it's a really important one. Then the viscosity, when you are measuring the viscosity suffers, and not only when you are measuring, when you are doing some process of polymers, they are suffering some common effect called wall slip. That effect is so important. Uh, Aside from that phenomena, we have another phenomena, another type of phenomena that I'm not going to talk about in this seminar, because mainly rheology is like huge topic and has so many stuff to deal with. Now we're gonna deal just with wall slip, because wall slip is so important in microrheology. Because in microrheology we're gonna start seeing how microrheology is useful for measuring viscosities and different properties of food processing products. Okay. Uh, then, knowing microbiology, we're gonna see the device, its principle, and the response. Here, you don't know yet what is the meaning of this, the startup, alignment, particle detection, and calibration. But this is so important stuff, because this behavior, this phenomena, is not visible when you are measuring in a bulk state, okay? So that's why in microbiology you will see, and I will explain it later. Then we're gonna test the device, measuring the common mayonnaise, the mayonnaise that we all use in our houses. We're gonna have the sample preparation, the comparison against the bulk properties, because this is in a bulk state and this is in micro state, okay? We're gonna see the yield stress and the wall slip that I will explain before. And then we're gonna compact all that information into a rheological state diagram. We want to see also some microscopic view of the samples. Then we're going to apply some measuring, some potato chips, the same stuff like mayonnaise, but instead of being mayonnaise are going to be some potato chips, the common ones that you can buy in a shop. And then the conclusion. So what is rheology? Mainly is the study and the formation of flow and matter of common complex fluids. It can be any type of compounds, emulsion, and suspension. Also, we have some food stuff systems. Uh, Also, they describe how the material can flow under different deformation and shear effects. The name of rheology comes basically because of the Greek word rheo, that means flow, and logia, that means study. So if we combine those things, it's the study of the flow. We're gonna see the common stuff that rheology studies, also Newtonian and non-Newtonian materials. Notice something that I have to put those numbers at the references in here. This is a really important book, and also I'm just putting some internet websites there. Those internet websites are from companies that creates the rheometers, and they used to work in parallel with universities to create a really useful rheometer. Okay. We have to see the products and needs. We need to know which scale is important for our cases. We have the molecular level, which is nanometers, and then we have the supramolecular structuring, in which we have food foams, emulsions, and food products and powders. Those are micrometers. From there, we have millimeters and centimeters. From here to there, we are on bulk state. From here to here, more or less, we are on micro state. Okay, we have to know which is our material, and knowing the material, we're gonna know the state that we are working on. So, bulk and microbiology. On bulk properties, the properties that usually dominate the materials are in a bulk state, which is in a huge level, more or less more than 100 micrometers. And from there we can measure the thickness, the firmament, the melting, and the breaking down of the molecules that they are suffering some deformation. Therefore, if we lower down, we are reaching to the 0.1 up to 100 micrometers, more or less. And in there, we are just measuring the creaminess, the fattiness, smoothness, and slipperiness. Something that I have to mention in here, this type of microreology is highly visible when you are, all of us, we use cream. You take a shower, you get out of the shower, as soon as you finish, you pass cream through the body. And when you are doing that type of shear on your skin with the cream, you see how it feels, the fattiness, the smoothness, and the creaminess. That's why microreology plays a role in there. So this is a stage, a really important stage. We're gonna talk about this stage and this stage, okay? And from there, we go lower and lower. We reach the surface properties. Eh, there are like nanometer stuff. I'm not gonna enter into this zone, okay? Well, the bulk and microreology. We have the common materials, which are liquids. Let's put it water. And we have some oils that they behave like a Newtonian stuff. And we have solids, okay? I'm gonna talk about this. But we have solids. Solids, we all know what is a solid in there. But something between them appears, and that's a viscoelastic stuff. We have a common gel, a common shampoo, common cream. That is a viscoelastic material. And in here, something happens that is like a mixture between a solid and a liquid, depending of the shear properties that you are, depending of the shear effect and the shear rate that you are applying there. Well, what is viscosity? Viscosity, we have to measure it. And what is it? I mean, it's the measure of a fluid's resistance to a flow. Uh, it's mainly like you apply some force, and depending of the force that you apply, you're gonna get a response. They are different from a Newtonian one and a non-Newtonian stuff. How to measure it? We have in chemistry the Cannon-Fensky. It works with a gravity. You put some solution in here, you have a mark, you take the time, and due to gravity, it lowers, you take the time, okay? That is measuring some type of viscosity, which is mainly Newtonian. Also, you have some Brookfield materials, which is Brookfield equipment. And that Brookfield equipment works with torque, on which you have a barrel, you have the liquid inside the barrel, you apply some torque, the system starts rotating, and then you start measuring the viscosity in there, because the resistance of the fluid with the torque, you get the viscosity. But that is mainly for Newtonian. Well, if we are talking about Newtonian, let's put it at this example. We have a tank, we have some fluid, the tank has a hole, it's connected to a tube. The tube has a specific part on which you have a constant temperature, constant radius, and of course, the pressure that you are applying is constant, okay? And you measure the flow rate. When you measure the flow rate, you apply all those values in here, because this is length, this is radius, this is pressure, flow rate. You apply all those values, and you get a viscosity. Nice. So what happens when you change the pressure? Well, the viscosity changes. And if that changes, is that a problem or is it okay? So the question still's in there. And everybody must start saying, okay, let's stick to the same pressure. But what about if we change just a little bit the pressure, not too much, and the viscosity changes drastically? Well, there is a problem that might be with the device, or is a problem that can be with the guy that was operating the machine. Well, the answer states mainly that the problem there is because of non-Newtonian system, but we're gonna see it later, okay? We have to know how the viscosity deals. And how can we deal with viscosity? Well, viscosity in a deeper understanding, we already know that the material force that passes through a tube and the resistance is basically the viscosity. But what about if we go deeper and deeper? Let's say that we have a wall, the wall of the glass or the wall of this wood, and you have some liquid, and the liquid is suffering this shear due to gravity, like the honey falling down or the water coming up because of some glass ices. They are coming up, and when they are coming up, the water starts sliding like type of a layer one to each other, okay? And when they are sliding at different velocities, they are creating some shear between layer and layer of water of honey. And as soon as you apply those, that shear keeps increasing or lowering depending if you are close to the wall or far to the wall. So let's imagine that now viscosity is a layer by layer of liquid that is attached to the wall, okay? Notice, in this case, we're gonna work with the laminar effects, okay? It's not turbulent because in turbulent we have some eddy effects that I'm not gonna explain. Just I'm putting this because state in mind that we keep in mind that we're gonna work with some laminar flow, okay? We have to know that viscosity and having the water keeps changing because of the layers that keeps increasing, okay? But well, what about if we go lower to the wall? As soon as we go lower to the wall is fixed, okay? This layer tries to move. As soon as it tries to move, the wall tries to stick and avoid the movement. So the shear is so high, the shear force, the stress is so high that it sticks mainly the layer and prevents the movement of the layer. So while we keep increasing in layers up, up and up and up and up, you will see how the stress lowers mainly in there. So as I mentioned, when the layer is close to the wall, it sticks, you have a large shear stress, and there is no motion, we're gonna have some effect that is no wall slip at all. We're gonna explain this term later. Then, when we keep going in this, the velocity profile of this layer is gonna be like this. As soon as you keep increasing in layers, you're gonna have this velocity profile, and the slope of the velocity profile is gonna be the derivative of the velocity that you apply at the beginning to move the fluid against the distance in this direction, in perpendicular direction to the wall. So that is gonna be the slope. In this case, as I stated before, as I mentioned before, the shear effect is higher in here than in here, okay? That's why you have this type of flow. Notice the slope increases and decreases as soon as you keep moving up and down, okay? When you are correlating those two things, the shear stress, that is this one, is close related to the slope, that is this one, okay? So if we go to change and analyze the graph, we're gonna see a line, basically. That is du over dy, and you have the stress. While the stress keeps increasing, you have du over dy that goes up, and you have a line. When you get the slope of that line, that is a viscosity. Okay, that viscosity does not change. Look at this. This is a constant. That is because we are working with a Newtonian system, and that's why the Newtonian one, they have a line. They have a line. If it's not Newtonian, we will not see how the system is. Well, we have some viscosity that is already constant, but let's see how do we get the other parameter that is important for the viscosity that is called shear rate, okay? That is important because later on, we're gonna talk about only shear rates and viscosities, and there is no more than that during this seminar, but I'll explain everything on detail. We're gonna have against the wall, the layers, and you have the distance. You see that this is the angle that we are suffering, and let's say that we're gonna take this small piece. We're gonna have this system, which is the former in infinitesimal part. We have a delta y, the velocity and a delta U. The delta U is from here to here, okay? Because this is an undeformed part and this is the deformed part that suffers some velocity in there. At some point, this point is gonna move to here. That's why we have the delta t. We're gonna have u plus delta u multiplied by delta t. And in here we have u multiplied by delta t. This part didn't move at all, okay? So in there we're gonna have some deformation, which is this rate. This is the strain. So doing some trigonometric analysis, we're gonna have the tangent of gamma, which is equal to all this part, which is the upper part, minus the lower part, divided by the distance in here in a y direction, okay? And something about trigonometric that in really small angles, because we are working in a really small part, in really small angles, we can consider the tangent of an angle equal to the angle, okay? So we arrive to this one. We arrive to this equation, okay? When we arrive to this equation, if we take and we leave only the delta u and delta y and we take delta t from here, we're gonna arrive to this equation, which is gonna be gamma divided by delta time, okay? Is equal to gamma of delta u divided by delta y. And in there is on which the shear rate appears, which is this one. You have the gamma dot equal to delta u divided by delta y. This shear rate is so important because this shear rate indicates that is the velocity, the rate of velocity which one layer is the rate of velocity on which one layer is higher than the other one. Is compared to one layer to another one in velocity. Mainly, it needs to be in adjacent layers. So now we already know the stress. We can calculate the stress, and we have the viscosity, and we have the shear rate. Okay. Now everything starts looking a little bit more like a non-Newtonian system, but still Newtonian. Okay. What about the non-Newtonian stuff? We all use different type of stuff like toothpaste, paint, and I will explain this one. Okay. This one I'm gonna leave it till the end. Okay. So we already saw that in the previous slide, in this one, shear rate is delta U divided by delta Y, okay? And we know that du over dy is equal to the shear rate. So we can place it in here. We have the stress, we have the shear rate, and in a Newtonian fluid, we have this blue line. What about in non-Newtonian stuff? Well, we have three types of system. One called shear thinning, one called shear thickening, and the other one called Bingham. Shear thinning is a common one, the paint. As soon as you keep increasing the shear rate, the line starts having some concave in downwards direction. You have some curve in a concave in downwards direction, and in there, I will explain this one in a really fast manner. You have some paint, you put the brush in there, and when you put the brush against the wall is staying with some part of the paint. If you take out the brush, the paint does not move. As soon as you start spreading with the brush, the paint starts spreading, of course, and that's a shear effect that you are doing on the wall. And as soon as you keep spreading even more and more and more, you are lowering the viscosity, okay? That's why you can paint the wall so easily. I'm not gonna enter in anything like a thinner and those kind of stuff that you mix on solvents. No, not those kind of things. We are working only just with simple paint. Shear thickening is this kind of stuff, and I will explain later, but it's mostly different. But we have the Bingham fluid. We all use toothpaste. When you want to brush your teeth, you are forced to press the tube of the toothpaste, any brand. And as soon as you press it, the material comes out from the hole of the container. The force that you are applying, you are forcing the material to flow. So that's an stress that you are doing in there. That's a yield stress. You have to apply some stress to make the material flow. As soon as you apply that stress, the material keeps flowing. If you don't apply that stress, the material never flows. Just test it. Put down just upside down, flip your toothpaste, and due to gravity, it never will flow. So that's why you have to apply that stress. That stress and that force is higher than the gravity. So that's a common material called bingham. Then you have the shear thickening, which is a really nice one. Just if you have at home, just take some cornstarch, mix it with some water. The mixture must be more cornstarch than water. The consistency has to be like quite thick. And as soon as you do that one, just put in a container, try to hit it really fast, and it will behave like a solid. Let it really slow and try to put your finger slow and slow, and you will see how your finger goes down. It behaves like a liquid-like. That is a common behavior of shear thickening. As soon as you apply high shear rates, the material presents a really high stresses. When you apply low shear rates and really slow, the material behaves so nice like a liquid. So that's why you have this kind of curve. Well, in here, we already know what is a Newtonian system. The Newtonian one, it means that the viscosity will depend always on the shear rate, but I never talk about temperature. I'm not gonna talk about in temperature in this topic, because as soon as we start entering temperature, viscosity start changing due to shear rate, temperature, pressure, and so many other factors. Like in many cases, you have some particles that you mix with polymer, and the particles gives some other viscosity, and there enters the packing fraction. So I'm not gonna enter in that. But the most important ones are the shear rate mainly, and then the temperature. So viscosity changes due to shear rate, yes, and viscosity changes due to temperature, yes, in non-Newtonian system, okay? From there, we have the steady and unsteady state that I already told you before that is going to be important one. A steady is a really fast example. Just imagine as a photo. You see the photo every single time, the photo never change. Okay, and unsteady state is called stress growth. Also, this is called startup. Okay, and that is like a video. The video changes due to time. In here, the photo does not change due to time. Um, let's say that you apply some shear rate, the initial one, and you see you have the zero. The shear rate is applied, constant one. You have some deformation. The slope is the shear rate in time, and you have some stress, okay? The stress is constant because you have some steady state through all this, okay? So this is like a photo. As soon as you change in time, you will see the same response every single moment. When you apply in a stress growth or startup process, you have no shear rate, and in zero time, you apply a suddenly response of shear rate, which is constant in there. In this part, you're gonna have the startup problem, the unsteady state. In there, you have the response going to zero, you have a deformation, you have the slope. But what about the stress? The stress might behave in three different ways, like going down, 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 and suddenly up, and then on a straight line, like a constant one. You might have this type of pattern, like keeps growing slowly, and you might have this type of way. And this one is so common, mainly on mayonnaise. You will see it later. Because in here, the system, the device, cannot apply straightforward the shear rate. The shear rate stays stationary, and the system tries to apply a really fast shear rate. So at that time, there exists this small overshoot that is so important, because if you are measuring something and you stay on this zone, you're gonna have different stress than this, than this, than this, and than this, and this. As soon as you let the material keep going, 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 and on and on and on, you wanna reach the steady state. Nice, but you have to be sure if you want to work with the steady state, or you have to be sure if you want to work with the stress growth or startup system, because the stresses are entirely different one to each other, okay? Well, we already know those kind of things. We have to talk how to measure the viscosity, and mainly the device. We have three types of devices. I'm going to talk about this one, the first, which is a capillary flow. It's like a barrel. You have a barrel, you have a piston, you put in there some amount of material, more or less 40 grams sometimes. I don't remember pretty well about that one, but it's more or less 40 grams. And you apply some force. You have an area, okay? You have an area, you have the radius, you apply some force. Of course, this is under constant temperature. When you apply that force, this is an enlarged part of this one. You have some pressure transducers in here. They are not showing it, okay? And when you apply that force, the material keeps flowing. And the material flows and creates this type of behavior. When the material comes out, the material expands. This phenomena is called dye swell, okay? The polymer swells after after it's coming out from the dye. That phenomena does not occur only on capillary system. When you are working on an extrusion line in any company that works with polymers, trying to inject something, they are or extruding something, they are suffering this kind of stuff. The material expands in a perpendicular direction to the flow. That's because of the whole molecules and the change. They are relaxing and they are trying to look for space. That's why they are expanding. This phenomena, I'm not going to enter in this because there are like several models and several ways to analyze, several ways to film it, several ways to check the behavior of it. Just something that needs to be clear, depending of the pressure and depending of the temperature, this response is going to be entirely different, okay? So be careful with that. This is a really nice graph of this capillary flow when you are like applying some pressure at the entrance, that is this part, and then you keep applying the pressure, the pressure needs to drop, and that's why it's called pressure drop. And when it's dropping, it will be nice to have a zero pressure drop at the exit. If you don't have a zero pressure drop, your system is not well analyzed, okay? Watch out with that one. dz and dz equal to L is the length of the barrel. Something that happened within these systems and also in the extrusions. When you are sending the material, this is a really nice figure. Those are simulations, okay? But it's already proved that it happens. The material keeps flowing, and due to this contraction that you see in here, you are suffering some vortices. And those vortices, what it's creating is like the material keeps flowing down, and those vortices keeps doing this kind of stuff, and it's creating a flow upwards, and the flow starts like fighting one to each other when you are applying some pressure, and the flowing going upwards because of the vortices. Those vortices can be controlled, can be minimized, and those vortices are present when you are changing the angle of the barrel. So there are some angles on which you have entirely 90 degrees. There is like a sharp angle. There are another type of angles like those, trying to minimize those kind of things. That is a problem that is still in the literature, and also is commonly visible in an extrusion lines. Well, in the capillary flow and the velocity profile, how it behaves compared to Newtonian with non-Newtonian. This is not only a capillary, as I already mentioned, can be in another processing system. Capillary is just a way of measuring viscosity, but it's like a representation of different type of process. And you have the non-Newtonian velocity profile that is like this, looks like a plug. And you have also the Newtonian one, which is this one, okay? And the shear rate, of course, changes one to each other. You see how different they are when they have different velocities in here. Well, we have then the measuring the viscosity, the device, the drag flow, the parallel disk. We have, compared to the capillary flow, we have 40 grams, and those grams, they are in a capillary aerometer, those 40 grams, and in here we have 1 gram. That is an advantage. Those are single plates. They are rotating one to each other, okay? One is stationary, the other one is rotating, and that requires less than a gram. We have no contraction angle compared to the capillary. The problem in here, This one, did you see, is a plate, and that's called parallel disk. Okay, a plate. When you apply some angular velocity, which is this one, and when you increase the radius and the gap, you will see how the shear rate changes. I want to show the formula, okay? Then we have the drag flow of the complete disk. And in here, we're going to have this type of angle, which is a complete, of course. And something quite nice that the shear rate is constant through the radius. I will explain the equation as well. Something quite interesting to mention in here, the manufacturing, we do not have a full sharp tip. We have a truncated cone tip system. The tip removal is having this type of geometry at the end, okay? It's quite difficult to have a full sharp tip. We have a limitation, the particle size. If you apply some particles with the polymer and those kind of stuff, it's so difficult because let's say that some particle sticks in here, so you cannot lower the rheometer even no longer because due to the particle. And you might have some fracture, some fracture at the edges due to high shear rates when you apply high angular velocities, okay? Well, those are the equations for a capillary rheometer. Do you see that we have an R minus 1? This one is the meaning of this. This is a huge correction, involves Mooney, Bagley, so many corrections that are required to measure the final viscosity in a capillary rheometer. When we are working with the parallel disk at rim, which is at the edge, we want to have the same R, and this is also because of the shear rate that I already told you that changes through radius. And check the shear rate. The equation is this: you have the angular velocity, you have the radius, you have the gap. The gap is this, okay? This is the gap. You have the gap in there, so you apply some angular velocity, and if you keep changing the radius from the center to the edge, you will see that edge remains constant, so this one keeps increasing. And what about in the complete? Because of the angle, let's say that you put some R in here and some H in here, they are canceling each other out, because as soon as you keep increasing the radius, the gap keeps increasing because of the angle of the tip. So that's why you have constant shear rate in here. Something quite nice, when you are measuring some rheology, you have some normal forces of the polymer. The polymer, it's applying some normal force from the lower plate to the upper plate. And in this rheometer, you can measure it. And those forces are so nice because those forces are also quite important for designing a new system or a new mold to create a product that we need. Well, the viscosity is the common responses. This is a common graph. The material, we do not care, okay? Just I'm gonna show you that the viscosity is measured in Pascal seconds and the shear rate in reciprocal seconds. You have zero shear viscosity, which is a common plateau, and then you have the shear thinning effect that I already mentioned before, okay? What happens when we compare them? This graph is so nice. Here, those guys, they presented. What they did, they took some water. The water is Newtonian, okay? And they start adding some polyester and ethylene acrylate latex particle in water. And when they are adding, they start seeing some kind of non-Newtonian behavior that you have zero shear viscosity lowering and then reaching a plateau again. But when you keep adding even more, you have zero shear viscosity, shear thinning, plateau, and something is increasing in here. Again, same stuff. Something is increasing in here. What is happening in here? Well, this is the shear thickening. This is the shear thickening. They are behaving more like a solid when they are suffering high shear rates. Look at this. Those are high shear rates, and they are suffering some shear thickening. So the material behaves more like a solid. This is so nice and visible, mainly on this one. You see? So this is a really nice example of the comparison of the two effects and two sides of the material. It can behave in one way depending on the shear rate, and it can behave in an entire different way depending on the shear rate. Well, we have the rheometer. This is a common rheometer that we already know, okay? This is the rheometer, this is the chamber, those are two plates, you plate the sample, you trim it, you close it, and you apply some constant temperature. This rheometer is from Anton Par. I'm not gonna do some marketing about those guys. It's Anton Par, and they are some others, TNA Instrument, Ares, and so on. Well, now we already know about viscosity, how to measure it, but we are suffering wall slip. What is wall slip? Is the effect that reduces deformation is caused by a large velocities, and what is causing is mainly the name of it, slippage, is sliding, and the sample means like it creates kind of a fracture. Take a look at this link if you want it. There is a video as well, and they see mainly how the rheometer suffers that. And when you have some wall slip, what is happening is that you have some shear stress, because actually you are applying a shear rate, that means shear stress, and you have some viscosity, the viscosity you are measuring because of the wall slip. When you measure with plate or comb plate with a smooth surface, the yield stress, because it's two phase, okay? The yield stress is at this point, okay? When you change to different geometries like this one, the hatch one, this is called a hatch. They create like a hatch, of course, some spikes through the entire area of the material. They avoid the wall slip, and you see the real yield stress, which is around here, while before was around here. So wall slip can create and can generate some fake viscosities, okay? That are not nice for the measurements, because if you have different viscosity, you can design your product for that viscosity, and at the end it's going to be entirely different. And that is a problem mainly on food. This is an explanation, okay? How the wall slip. You have the velocity profile that I already explained before, and then when you have the velocity profile with a slip, you see that the last layer that touches the wall suffers some slippage, okay? While in before, I said that you have no slip behavior, but in here you have a slip behavior, okay? Well, we have problems with the bulk rheology nice. I already explained those. But what about with micro rheology? We have the complex fluids, polymer mills, food, processing, consumer products industries. But the boundary effects like wall slip, the scale, also the impacts on the size of the sample, mainly because of particles, we cannot measure in bulk. We have problems, some difficulties on this rheometer. We have difficulties if we try to lower the gap, as already mentioned before. When we are just sharing the cream on our body, the thickness of the layer that we are sharing is not a millimeter, it's less than a micrometer, it's less than 100 micrometers, even 1 micrometer. So those rheometers that I'm presenting, these ones, they cannot go in a really low gap. So we need something more to measure those kind of things. And that's the solution comes the flexure-based microgap I will show it to you later on how it is. We have the samples. The samples are on the size, really small. We have the gaps. The gaps can be from 200 up to 1 micrometer, okay? This is the rheometer, the principle. You have two flexures. You have the sliding plate. But this sliding plane, when you apply some stress and some displacement, this one goes up. So we need to have another two flexures. And that one, we can calculate the constant spring with this simple equation. Notice, this system was created by my professor at that time when I was in Belgium in Leuven, Christian Classen. He was doing his postdoc, as far as I remember, in MIT, and he created that device. Then he took the same principle and applied it into Belgium, and yeah, then we use it in there, and I use it as well. And the system is, like as I mentioned, really quite simple, but it's so nice to use it. This is the rheometer. Well, you have the detection spring. You apply some. You have the motor. The motor keeps shearing in here, and the motor applies some velocity. This spring detects the motion, and from that one, we're gonna know. This sensor detects the motion, and with that, we're gonna know how the sample is suffering and the viscosity from it. Also, something nice. There is a light that is passing through it. That light is helped to use the alignment, the calibration of the material. Those tilted fringes that you see in here are useful to see if the plates are parallel. If they are not parallel, they are tilted. This is mainly the rheometer. You have one plate in here, you have another plate, you have the motor. They flip it back, okay? They flip it, and they have the motor. This applies some shear, this stays stationary, and you have the sensors, okay? Those sensors are highly useful for measuring the displacement that suffers the other plate when you are shearing, okay? Well, the rheometer, the response. And here we're gonna see the startup process, okay? We have the sensor spring displacement that I already mentioned before. We have the shear stress. When you apply it over certain time, you're gonna see a sawtooth wave. Look at the stress. Goes up, creates an overshoot, then reaches and stabilizes steady state. This is the startup process. The other rheometers, the common ones, they do not measure this process. This startup process is no longer measured in the other ones, but this rheometer is able to measure it, and then we reach the steady state. And in here, we're gonna see which part is important for us, because if we don't see this kind of graph, we might play on this zone and we don't know it. But now we know this graph, and we know on which part we are working on. The shear rate is measured, as I mentioned before, velocity over gap, which is the distance. That does not change. The same formula, the same equations, and from there we can know easily the shear rate. Okay. The micrometer, the alignment and the particles. Something nice aside from the light being useful to align the plates and parallel one, is useful to catch particles, detection of particles that are close to the surface. And that is so nice because you can see how the particle moves or breaks down or tear apart when you are shearing, and you will see how the viscosity drops or increases when you are shearing, because you will see the actual particles. Okay, I'm gonna show it to you later on. Some calibration. I'm not going to explain too much on this, just I'm going to show something in here really fast. He was using, Professor Christian Klassen was using all those gaps to compare to the common bulk rheometer, because this is a bulk rheometer, stress control, complete, and yeah, this is the response. This is a common Newtonian material, okay? Polyethylene melt. But here we have a no problem response. This is because of the gap. The gap was so low, and there were like some dust particles on the air. If we place the device in a room that is free, dust free, you will have that behavior will be gone. Okay, but we see that all curves overlap as one to each other. Well, the samples, the mayonnaise and the complex fluid. Professor took some mayonnaise, which is one called natural and has some fat, and the other one which has fat-free, okay, has no fat. And those are the components on each mayonnaise, okay. Later on, we have to see that you have two components, one mayonnaise which has fat-free and the other one has fat. When you buy a product that is fat-free, you expect the same flavor as the fat one, okay? When you have that one, you need to create a product with the same behavior when the people is eating it. So let's see what are the responses of those. The samples are refrigerated, and they are put it on the rheometer, let it cool down in there and relax for 30 minutes. Then the material is sheared, okay? The results in there, we have the common vein system, we have the bulk one, and this is for fat and fat-free, okay? And this is for the bulk. When you apply some lower gap with the bulk rheometer as well, you have those type of problems. And they are not overlapping one to each other. This is on bulk, okay? But what about when we apply the other rheometer? Look at this. This is like overlapping, and we have some not overlapping in here, and this is the yield stress. Do you see, as soon as we keep lowering the gap, there are overshoots? Those are yield stresses. Okay, when we take that graph, we're gonna see the yield stress as soon as we keep lowering the gap, the yield stress keeps increasing, okay? What about with the fat-free? The fat-free has, all of them are overlapping and no yield stress. But wait, further in some shear rate, they are separating, having like type of Newtonian stuff, and there is some slip layer. Through all these equations, we're gonna catch the final slip layer. All those equations represent those graphs, and finally we're gonna see the thickness of the slip layer. And we see that the slip layer is highly present after 150, more or less 158 of shear stress. If you keeps increasing that shear stress, you're gonna see the slip layer through the walls of the rheometer, okay? Secondary yield stress, sorry, you have secondary yield stress when you apply those kind of things. You have the primary yield stress that I showed to you, but if you keep applying some shear rate, you have secondary yield stress. That secondary yield stress means like, okay, already you overpass some part of the sample due to force, but then you are like type of breaking apart some particles and those kind of things. There are no motion of the layers on the first yield stress, and in the second yield stress, the motion is entirely full in there. That mainly occurs when you are lowering the gap in the fat. When we compact all those kind of things one to each other, we're gonna see how the yield stress lowers. We wanna have some four regimes, the plastic behavior, which is in here, the flow between stick layers, which is in here, that I already told you that is the second yield stress, the pure flow, which is in here, that flow you saw also on the fat free that keeps flowing, and you have the flow with wall slip. This is the 158 shear stress. After that one, you will have wall slip. You compact all those, and with this nice diagram, you will see. You don't need to see the previous graph. With this one is good enough sometimes. Well, the yield stress explanation along with the camera. You have some fat-free, no, sorry, fat material with the mayonnaise with fat, and you see the particles, big ones. When you are lowering the gap, those particles, they are compacting one to each other even more. That's why you have a sudden increase after lowering the gap lower to 20, okay? Those gaps are filled entirely, probably with some particles of mayonnaise. But what about with fat free? You have no those kind of particles, so that's why you don't have the gap dependence, and that's why you don't have the yield stress in there. Well, when we see the microscopic view, you see how the microscopic view, when you are shearing at the beginning, you see those spikes, there are particles, you apply some shear cycles, and then after 15, I remember, I think that is 15 minutes, more or less, you see how the particles, they start shearing and they appear more. The particles can break down, or the particles, they compact even more, and that's why you have how you can see that one through the rheometer. This is so nice because after a while you're gonna see some plateau that probably later on lowers, okay? And see the density how increases and stabilizes at certain point. Well, in here in results, the potato chips, that was with mayonnaise. These are potato chips. Let me just put something clear in here. I cannot show you to you old stuff because when I was doing my master's, that project involved some other companies, and yeah, you have some contracts on which you cannot show so many things. But I use some potato chips. The potato chips I grind them with a turbula mill. They have some zirconia balls. The zirconia balls, they have these dimensions, and they do not create heat. They start shaking the container. They have the potato chips. They are grinded, and they end up giving this type of results. You have the potato chip particles that are these ones, really small. They are not circular at all. They are not spherical, but you have water, and also you have oil droplets. You have three components, so this is gonna be quite difficult to characterize. Then I decide to perform some particle size. dimensions, and all of them at that case, I just took one graph, is 4.6 micrometers, okay? Then we lower we start performing the shear rate at, of course, at really low shear rates, and we see that the shear stress does not change. There is a plateau. But then if we apply some apparent shear rate and we obtain the shear stress while we are lowering the gap, we see how the shear stress keeps lowering while the gap is increasing, okay? Well, if we take those plateaus and we compare the potato chips with this one is the low oil content potato chips, and this is the normal one, okay? And if we see in here with the gap dependence, we see that they are more or less overlapping one to each other in 7.5. What about in 2? They are changing, but they are reaching one to each other at higher gaps. It means that at bulk rheology, again, we cannot see those type of behaviors, okay? In 2%, in low oil content, we have this one. And with a high oil content, we have this behavior in lower gaps, okay? While in the other rheometers, we cannot see it. The problems that we saw, it's impossible to achieve those to overcome those kind of things. The particles, look at this. This is 1 centimeter, and we have some aggregates. Look at that. This is 1 centimeter of aggregate. Impossible to measure that one in the rheometer, okay? And the gap never stabilizes. The conclusions. Well, we already know the bulk rheology is highly useful for polymers. The samples, more or less, are in 40 grams in the capillary, while in the other ones can be less than a microliter. Bulk rheology can measure some food problems, yes, but it's so difficult. In many cases, you have to lower the gap. When you are lowering the gap with the common rheological rheometers, they have problems because there is a gap error correction that you have to perform. You don't know if that problem might persist later on. Your results can vary one to each other every single time. That's why gap dependence is not so easily to perform in a bulk rheology. But in the case in a flexure micro-based rheometer, you can characterize those kind of problems. You have the gap dependence so easily. You can characterize the wall slip. You can characterize the yield stress. Notice, I'm just talking about now about the food industry, okay? Because in common polymers like PLA, ABS, polypropylene, you can characterize them so easily with a common rheometer, okay? You don't need to go to the flexion microbase. That rheometer is mainly for food products, cosmetics industry, those kind of things. The common rheometer didn't catch the startup process, while in the microbase, yeah, the startup was catched. You saw how to overshoot, and then the stabilization of the other parts. So I present to you the unsteady and steady state. Then lowering the gaps, it helped quite a lot. And the errors in the microbase was not visible. The only one was the dust that I already explained to you that if you have a dust-free place, that problem will be erased entirely. At this moment, the problem with the flexion microbarometer, well, not at this moment, at that time when I was using it, it didn't have any temperature control. But can be useful and cannot be useful because the food industry, as I already mentioned it, the cream, you are using the cream at room temperature. The mayonnaise you are using in that room temperature. So that's why my view might not be, because depends on the situation, okay? Aside from this one, something cultural that I want to show to you is something that is about rheology. This is just this slide. It's so nice. There is a pitch viscous material. The pitch, instead of calling pitch, you can see and go the asphalt. It's asphalt basically. there in the University of Queensland, there was this professor partner that he took some pitch, put some container at the bottom, and he started measuring the pitch drop experiment in there. And the drop, only as far as I remember, is, it says, after 87 years of the funnel was cut, what he did was put in the pitch. After 3 years, yes, I remember pretty well. After 3 years, he cut the steam, and from there he started measuring how long it takes to to a drop fall down in here. And during 87 years, only 9 drops were recorded. There is a camera in there. You can check the website, University of Queensland, and there is also a YouTube video in which you see how the drop keeps falling. It's a material that can be solid because due to our eyes, we go to the asphalt and we see that it's solid, but it flows. So the question is still in there. So we might have material that might be liquid and solid at the same time. And well, take a look at this if you want it. This is just a cultural view. And that's it. Obrigado, thank you, and gracias. Sorry for not presenting in Portuguese because my Portuguese is not so good. Okay, thanks.
So
Hello?
thank you so much for your presentation, Alberto. It's a pleasure to hear from. It's a really expert. You are really expert in this theme. I'm so happy to hear your seminar because you have a lot of interesting results, and this is very, very important for materials. Everybody who works with materials should know about that, you know. I feel that you missed to say something concerning the solid materials. Because you can characterize solid materials by shear measurements. Indeed, there is also a definition. In some books, there are some definition of solids, a solid material, in function of the shear viscosity. Could you talk a little bit about this? For example,
Yeah.
do you remember this definition of a solid from shear viscosity measurements?
Yeah. Let me. Yeah, I saw it, Professor. There is.
It's not
There is a. Is it because probably you saw in some books, and also I saw that they say there is a creep measurement. Creep measurement, okay?
Okay.
And they perform creep measurements on liquids and in solids. And the question in there for all of us arises, I mean, is the creep measurement right for solids? Is the creep measurement right for liquids? Is the material solid or liquid? I mean, the definition cannot arise so like popping up, and you have the definition straightforward. I mean,
there is a definition that when you apply a shear strength and the material does not present any deformation or a deformation with a very, very slow number, it can be defined as a solid material, there are some books that brings this definition concerning considering the shear measurement, So I think this is important because it's a very general explanation, definition of solid, but it exists, So I think, actually, for everyone who works with materials, you should know at least the principles, the fundamentals of materials, mechanical properties of materials.
yes.
I agree. Do you agree?
Yeah, I agree. No, I agree. I entirely agree with those kind of things. I mean, they have to know at least the solid stuff and the fluid stuff. In the most basic one can be Newtonian, and the solid one can be in an elastic way. I mean, just with those, I think that is good enough. From there, you can move on.
Okay. And in your PhD project, do
Yeah.
you work with any kind of measurements of shear viscosity?
Well, viscosity now, not at
No.
all. It's not related at all with my project. This kind of stuff is out of my topic entirely. I mean, I'm
Okay.
working entirely with solids. I'm
As
working with 3D
expected
printing.
for as
I mean,
expected for a seminar here, yeah?
yeah, my project is about 3D printing and extrusion stuff, but I'm not measuring any viscosity. I'm just measuring the solid stuff, tensile, compression, those kind of things. Nothing at all about
Okay.
viscosity.
Okay. So, Professor Horácio, do you have any question? And now, or you can start to see the questions of the students.
Starting from Augusto.
We can start with the questions of the students. Yeah?
Yeah.
Okay, let's go. So, are you reading? Yeah, Alberto.
Well done, your presentation, Alberto. What techniques
Presentation.
quantify wall slip in non-Newtonian fluids in confined geometries? How the fluid and properties and geometry affect wall slip? In confined geometries. Well, there is something quite interesting in there. The, there are techniques for quantifying the wall slip. There are, in theory, theoretical way, you have several ones. I show it to you one like two equations, but you will see in a common rheometer. You take a common rheometer, you apply high shear rates, put an emulsion in there, and you will see the wall slip entirely. Put some mayonnaise in there as well. Just put some mayonnaise, really small. You will see the wall slip entirely. When you put some particles, I remember that I don't want to mention the brand, but I remember that one company that create toothpaste put some particles in the toothpaste while you were brushing, and you felt those particles on the teeth. I remember that was a company that put those kind of things. They performed the shear stuff, and the wall slip was present. Those particles, they were sliding one to each other. Okay, they were sliding one to each other. They aligned it and they faced wall slip. That is a common one with some emulsion and material that they have particles. The geometries, I mean, you put some powder in the fluid, and when you put the powder in there, you will see probably wall slip. They affect it. And you create some hatch sometimes in the geometries of the rheometer, and yeah, the hatch helps to prevent the wall slip. But you will see the wall slip mostly in any rheometer with just, of course, if you are measuring some PLA ABS, you won't see the wall slip. But if you are measuring some emulsion or some cream, some mayo, some food product, mostly you will see the wall slip. Probably you, all of you that as a chemist, you know more about those kind of things, emulsions and solutions that you measure, and you will see the wall slip in there.
Okay. So, next question is from Enivaldo. One of the limiting factors for a greater application of polymers in the automotive industry is low resistance, high deformation. Does your work have any contribution to minimize this problem?
Well,
Which kind of work your
I'm
PhD?
assuming that these masters. I'm assuming that one. Well, my master was about those kind of things, but the topics that I got in the masters, they were like a extrusion of polymer processing. And I remember that in Portugal, the university, they are polymer processing, extrusion, injection molding. They are working with those kind of things. I work with those. I know how to deal. I know how to work with those kind of things. But that, as I already mentioned, that's in bulk. And yeah, there are kind of things that they are working with the minimizing the problems of deformation. Just to mention, there is some PEEK material, PEEK. That material is so nice for high resistance due to impact, and the people, what they are doing, the common machines, they are trying to create some prostheses for people that, so let's say that you break a bone and they have to cut it out some part, they replace it, and they are using this kind of material because the deformation is so low, and also the resistance is so nice. There's an example, okay? There is an example, but I mean, you can work with common materials just with the nice setup and parameters of velocity, extrusion, and shear rate. And if you can control those, you can have a product on which you have to say this product is able to resist from here to here, okay? No more than that. It's up to the user if he wants to go further. It's up to the user that one, but yeah, there are people working on those.
Gabriel, are the fluids that change their viscosity over time, they are more viscous and they are less viscous, and then they return to the previous viscosity? I think it's the temperature, isn't it?
Because the temperature has an impact, no? You have some temperature. If you increase the temperature, yes. If you lower the temperature, yes, you have a change. But as far as I remember, by itself, is the stuff that I was saying, the Bingham fluid. There is, I think that there is a toy for kids. There is a silly putty. In Portuguese, it's massinha. And that one, if you let it by gravity, just hold it by gravity, it starts flowing by itself. Or put it in a table, make a ball, put it in a table, and it starts flowing by itself. Just make the ball and hit it, and it starts behaving like a solid. So the viscosity increases in one way, and the viscosity decreases in the other way. But that involves gravity. I mean, it's because of gravity, basically. That's a Bingham stuff.
Okay, Talita, congratulations for your presentation. How to measure device viscosity, capillary flow in complex systems?
Complex systems. Well, let me just tell you that if you say that a complex system like an emulsion, some cream, some kind of mayonnaise, mustard, food processing is basically, I haven't seen it yet. Because actually the capillary is mainly for the industry of polymers like plastics. Those glasses, they have a polycarbonate, and they measure the polycarbonate with a capillary stuff. So it's mainly for those kind of plastics. I haven't seen in a capillary rheometer yet, because I'm a little bit out of that topic nowadays. But I mean, at that time, I never saw it.
Okay, Rubens, there's a question from him. Congratulations on the presentation. Is there a direct relationship between shear and temperature in the preparation of polymeric materials?
Yes.
Things both influence viscosity?
Yes. There's a direct influence, yes. And also, I didn't mention it, because if I want to mention, I want to enter in a, I mean, rheology has a lot of stuff, but there is something that is a viscosity dissipation. That viscosity dissipation, when you apply some shear, you increase the temperature. And that is so common in an extrusion machines. You have an extruder, there is a infinite screw. The screw keeps increasing in diameter. Is closing while it's increasing. This is the wall of the tube when it's passing the screw. When the screw keeps increasing, the shear rate close to the wall, because of the increase of the radius, is so high. It means that the shear rate is high, increases temperature, lowers viscosity. So shear rate and temperature playing both, one can create more temperature, and the temperature can create the shear higher as well. So there is a direct relation between those things, and affects entirely the viscosity.
Okay. The next one is from Luan. Congratulations on your presentation. How can the information obtained from a microhyometer be used to optimize the formulation and manufacturing of
The mayonnaise.
mayonnaise?
They were like, I showed you one graph like this, and that graph have all the fat, the mayonnaise that we're measuring with fat, and the other one that has fat-free, okay? And I said that the yield stress in the fat changes because they had an overshoot. And in the fat-free, the material didn't change. And it followed the actual bulk response on the rheometer because they measured the same mayonnaise on bulk. And those graphs, they overlap one to each other. So if they overlap one to each other, it means at that time, at that stage, it means that the formulation was correct, okay? Was correct. If the graph changes from the bulk compared to the bulk, the formulation is not correct, okay? But something more important than that, it has to be that the rheological response, like viscosity and stresses and yield stress, they have to behave, the fat-free, they have to behave the same as the one with fat. Because when the consumer, when eat it, all of us, we are like, we want a product that is so good that you say, okay, I bought it, the one with fat. Now I want to buy it with fat-free. And we all of us say, fat-free is so bad. We like the one that has fat. So that's why the fat-free has to simulate the one with fat. And I showed as well some images, the microscopic ones, that I said the gap dependence, you have some particles in the fat-free. The gap dependence is so present in here because of the particles, and the fat-free has no gap dependence, means that it helps even more. Having the removal of those particles it helps to the avoid of the gap dependence, and it simulates the one that has fat.
Okay. So, Rafael, Giovanni say congrats. Can external interactions such as magnetic or electrical fields change the viscosity of the material?
Yeah. There was a guy, my colleague, when I was doing my master's from India. That guy was working with. That was 2015, and yeah, there in Belgium they were trying to replace the wires, the copper wires with polymers that has some dielectric responses, and they were measuring the viscosity, and yeah, because of that, the viscosity changes.
Okay. Luisa, congratulations for the presentation. Why not use the Taylor Coet device?
That actually the rheometer, the flexion microbase gap rheometer took the idea from the Coet Taylor. The Coet Taylor is no longer than a tube and another cylinder that enters. The cylinder that enters into the tube contains the sample. This cylinder enters in contact with the entire sample, and the gap and the shear rate is the same as having those two plates. The problem with the Coet, the sample, you need more sample, one stuff. If you want to change the gap, you have to change the entire stuff. So let's say that you want to stay in 200 micrometers and you want to lower up to 5 micrometers of gap. So you need so many components to place in there, lowering 1 micron, 1 micron, 1 micron. And at some point you will have so much error in there. While you are lowering the gap in the rheometer that I explained, you are lowering at some point at the level that you want it. In the other one, you have to replace and put the other one. Change the sample, put another one, and yeah, that involves so many errors.
Deborah say congratulations for your presentation. Thiago say congratulations for presentation. Alberto. Thelma say congratulations for presentation. So these are the questions and comments we have here. I'd like to know if Professor Horácio would like to make some questions.
No, not one question, but one curiosity. If you change your polymer with a lubricant, what do you think about the changes in your experience with rheology?
Wall slip, I will see it entirely. You know why? There are like people when they are extruding polymers, common polymers that are so dense and so heavy to push it. So even in many cases, extruder machines, common extruder machines, are already broken because of that type of polymer. And the people used to say, okay, it keeps increasing temperature. Okay, if I increase in temperature, I degrade it. So they said, put a lubricant. And the lubricant, what it creates is like a small wall between the wall that you are extruding in this wall. There is a lubricant in here and a lubricant in here, and the polymer passes between that lubricant, and that creates a wall slip, helping the material to flow and extruding. Helping the material to flow and extruding. Then, of course, the viscosity will drop. The viscosity will drop. You have to control that. That is not something that you are avoiding. You have to control it, but you will see some wall slip in there easily using the lubricant. Okay.
Yeah. Oh, nice, nice talk. I think that it's an uncommon subject in material science, and it's very important also. I saw the tendency to get the 2D materials is based on that. You have, for instance, you have a graphite which can be used there, and you can use rheology to get one monolayer of graphite, which is graphene, which is very important.
Yeah.
I asked about the lubricant because lubricants is also being an interesting subject, like, for instance, the molybdenum disulfide, which is a lubricant. And everyone here in electronic materials are looking for that, how to deal and make a 2D materials with those materials.
Yeah.
So it's very important to see what you can do with rheology in these cases.
Yeah.
Starting with polymers, of course.
I agree.
So, Alberto, I have one more questions for you, since you are an expert in shear viscosity. How can you explain thixotropic property of a material?
I avoid that.
If shear,
I avoid it.
Okay.
I avoided because that wasn't my strong. That wasn't my strong topic, Professor.
Because we are doing some extension, so
yeah, thixotropy. Thixotropy is.
Yeah. If possible, please just say, how do you understand it based on your knowledge about shear viscosity? How could you explain thixotropic property?
I showed to you that in the graph of Newtonian stuff, you have the shear thinning, the shear thickening, okay? That shear thinning is also called pseudoplastic material. The pseudoplastic material, when you apply some shear, you are changing the viscosity and so on. When you release the shear, the material needs to go back to the original state at the beginning. So that's why you are doing like kind of a cycle in there. In the other one, in the dilatant, which is also called shear thickening, you have probably the similar behavior. But there are cases on which the material does not come back to the original state. So that it is a shifting that you are suffering when you are applying that shear. Thixotropy plays a role in there. As I already stated, I'm not an expert on that. As far as I remember that one, I avoid it. It's a really hard topic. It's not something that say thixotropic is this one, because many people mix thixotropic with loading and unloading, and it's not that one.
Yeah.
It's not that one. Okay, it's something that I have to mention. It's something that has to deal with the molecules and the change. And Is the only thing that I remember, Professor. You already catch me. You already catch me. You already got me.
Yeah, it's a topic that you might consider for a next presentation. You're going to talk about this theme. Probably you may mention it. Just mention it. I think it should be important, don't you think?
No, it needs to be mentioned. I mean, it needs to be mentioned. It's always important that. But I mean, what I thought at the beginning, I said like,
I know it's a complex theme, so, but I think I'd like to know about your ideas about that.
no, it's okay. But you got me, Professor. You got me. I mean, I'm so weak on that.
Just another
But you
curiosity.
can get stronger.
Yeah, I will.
Another curiosity. You talked during your seminar about potato chips, which come from the Pringles. Pringles, isn't that?
It's not a
my
company.
question is another. There's an interesting Minas Gerais product called torradinha. Did you try to think what is going to happen with the torradinhas?
I mean, that topic. I was in Belgium there, doing those kind of stuff. So
no,
the
Belgium
company,
and Holland is famous about potato chips.
They got those packages, né?
Yeah.
Even the bag was that like metallic one. It had no brand, but I know the brand, but I cannot mention it. Okay,
Sure.
I know the brand, and yeah, they had the brand, and they gave me the potato. I did my work. Okay, fine, but those kind of stuff that you are mentioning, while I was in Belgium, they were playing a lot of things with different foods. It's not you are mentioning that one, but I remember that there was one guy that was measuring the foam of the beer, because Belgium is also playing with a lot of beers.
Yeah.
Belgium is so famous with beers, and he was playing with the foam of the beer. And aside from that one, they were playing with some pesticides as well. They are playing with a lot of food, with pasta, and I mean that the product that you are mentioning can be also measured. And pretty well that can be measured, because when you are eating those torresmo and you mix it with saliva, you start grinding them. What is happening with the teeth is doing this kind of shear processing. It lowers and does this. And when it lowers and does this, you are grinding the material, mixing with saliva. But some part of the fat, that the oil of the fat of the chip, of the particle chip, covers actually the chip. And the saliva goes around it. If you put some water and with that chip and oil and you let it flow, automatically it will separate. I mean, we all know that, but with saliva, it does not separate. We have to use artificial saliva in many cases. In my case, I use water, but if we use artificial saliva, can be measured. I'm pretty sure that can be measured.
Okay.
Yeah.
So I'd like to thank you so much, Alberto, for your seminar.
Thank you very much.
Thank you, everyone, for watching. And I wish a very nice weekend for everyone. And we are going to close this transmission.
Thank you very much. Have a nice weekend. Ciao, ciao.
Ciao, ciao.
Ciao, ciao, everyone.